Okay, so today is the last lecture in the series on differential equations, the denouement as it were of the course, and we shall continue first with the study of Bessel's functions, and we shall derive the integral representation of the Bessel's functions, and thereon we will move on to a problem in celestial mechanics and see how Bessel's functions appear very naturally in or rather not so naturally, perhaps rather dramatically, I should say, in the analysis of the problem, mechanical problem. Okay. So the theorem that we are trying to prove, that we are going to prove today, is the formula is to obtain a closed form for the generating function for the Bessel's functions. So remember that we have the Jnx for integer values of n, and when n is a negative integer, we define Jnx to be minus 1 to the power n j minus 1x, correct? That is taken as a definition. So with that I have the Jn for all integers, and now I write down the generating function sigma n from minus infinity to infinity Jnx t to the power n equal to x of tx upon 2 minus x upon 2t. This is going to be true for all t not equal to 0, this formula is going to hold, okay, and for all x. All right. So let us proceed to the proof of this formula. The formula is due to Schlumilch. So let us write down the sum of the series as f of x comma t. Let us differentiate with respect to x. What do you get? Sigma n from minus infinity to infinity Jn prime x t to the power n. Of course, we must justify term by term differentiation. That let us postpone the discussion on that and let us carry on the proof. With the proof. So Jn prime is what we saw yesterday. I gave you a list of 4 simple exercises, right? Relationship between Jn, Jn minus 1 and Jn plus 1. There are 2 relations and those can be recast, one of them can be recast as Jn prime equal to 1/2 of Jn minus 1 minus Jn plus 1. So use that, get rid of the derivative of Jn and write it in terms of Jn minus 1 and Jn plus 1. So here we are. So this is the formula that you get. Now you just separate the separate it into 2 series, okay, and then shift the integer. In the first one pull a t out, in the second one introduce a t and divide by t, correct. So that again you are getting t by 2 minus infinity to infinity Jn minus 1 x t to the power n minus 1 minus 1 over 2t sigma n from minus infinity to infinity Jn plus 1 t to the power n plus 1. Okay. What do you get on the right hand side? T by 2 minus 1 over 2t f of xt. Is it clear? Is the argument clear? It is a straightforward term by term differentiation and using the recursion relation between Jn, Jn minus 1 and Jn plus 1, right, and we get this equation del f by del x equal to t by 2 minus 1 over 2t f of x. What is this that we have just obtained? It is it looks like a partial differential equation, but really it is an ODE, because t is just, think of t as a parameter. For each fixed t, right. So what is this? This is a first order linear ODE. It is a first order linear ODE, and we can immediately write down the solution, right, and the solution is nothing but f of xt equal to f of 0t e to the power tx by 2 minus x upon 2t, correct. Alright, now we have to calculate the constant of integration, right. f0t we have to calculate now. We have found that f of xt equal to f of 0t exponential of tx by 2 minus x by 2t. Or what remains is to show that f of 0 t is 1. How will you calculate f of 0 t? Put x equal to 0. Put x equal to 0 where? In this. Over here, put x equal to 0. Correct? Put x equal to 0 here. Now, what is jnx? What is jpx? Jpx is x to the power p into a power series. Correct? Jpx is x raised to the power p into a power series. So, when you put x equal to 0, what happens? Jpx is 0 if p is bigger than 0. Correct? So, Jn 0 is going to be 0 for all n greater than or equal to 1. J1 0, J2 0, J3 0, they will all be 0. J0 of 0 is what? 1. Exercise, J0 of 0 is 1. What is J minus n of 0? Minus 1 to the power n of Jn naught. J sub minus n, J minus n of 0 is minus 1 raised to the power n into Jn of 0, but Jn of 0 is 0, no, for n equal to 1, 2, 3, etc. So, what do we get? When you put x equal to 0, what do we get? All terms disappear except the n equal to 0 term. N equal to 0 term is 1, J0 of 0. J0 of 0 is 1, correct? So, what is f of 0 t? F of 0 t is 1. F of 0 t is 1, and then we get we have determined f of x t equal to e to the power t x upon 2 minus x upon 2t, correct? The derivation clear? So, what is left over now? What is left for us to do? To justify the term by term differentiation. Now, suppose you take an infinite series, sigma fn x, sigma fn x n from 0 to infinity, 1 to infinity, whatever. If it is minus infinity to infinity, then you just break it up into two series, right? 0 to infinity and minus infinity to 0. Minus infinity to 0 replace n by minus n, and so we get essentially two series, right? We have two series now, sigma fn x, t is just a parameter, think of t as a constant, t is just a parameter, so fix t, okay. Now, what do we want to do? We want to say that ddx of sigma fn x, ddx of sigma fn x equal to sigma ddx of fn x. We want to take an infinite series and do term by term differentiation. When is this valid? When can I do that? If the series converges uniformly, that is what you think. Well, not quite. Let me give you a simple example. Sigma sin nx upon n, sigma sin nx upon n will converge uniformly on the interval pi by 6 to pi by 4. Let's take some small interval not containing the origin, or okay. Take pi by 6 and pi by 4. In that piece, sigma sin nx upon n will converge uniformly. The series of derivatives does not converge uniformly. Does not matter. You just differentiate the series term by term, the n comes out. See, what is happening is that uniform convergence means what? That the amplitude, suppose the modulus is all less than mn, right. So, the amplitudes may be small and the series may converge, because the moment you take the absolute value, you get things may become small, but then the frequency may be pretty large. The frequency may be pretty large, right? And so, when you differentiate, the frequency comes out, no. sin omega x. When you differentiate, omega comes out. You could have a high frequency business. So what is uniform convergence basically? You have fn's converging to f. What does it mean to say that fn converges to f uniformly? You draw the graph of f. Draw the graph of f. Okay, take the interval, let us say AB. Draw an epsilon tube around the graph. Draw an epsilon tube. Fx minus epsilon, fx plus epsilon, right? Draw an epsilon tube around the graph, and all your fn's, the graphs of fn's must be inside this epsilon tube for all n bigger than or equal to n naught. Correct? So you could take an f, you could take the epsilon tube around it, correct? And the functions may be inside the tube, but they may be highly oscillatory and still be inside the tube. Correct? Take 1 over root n sin nx. Take 1 over root n sin nx. What does the sequence do? It converges to 0, a sequence, right? So you take the 0 function, take a small epsilon tube, and 1 over n is your amplitude, right? The amplitude is small. So when n is large, the graph of sin 1 over n sin nx is going to be inside this epsilon tube. The amplitude is small, but the frequency is large. Frequency is n. So when you differentiate, you got n cosine nx upon root n. So you got root n cosine nx. Amplitude has gone. So you see, uniform convergence cannot guarantee that a limit and differentiation can be exchanged. The correct conditions are, if fn converges to f, let us say pointwise, listen carefully, fn converges to f pointwise, fn prime converges uniformly to, let us say, g, then the original fn's actually converge to f uniformly, number 1. Number 2, that limit function f prime is the same as g. Correct? What is the condition again? Let us go over it again. You are given a sequence of functions fn converging pointwise to f. Alright. The second hypothesis is that the sequence of derivatives converges uniformly to some function g. Then the original sequence also converges uniformly. Fn converges to f uniformly, and f prime is your g. That is, term by term differentiation is valid if the sequence of derivatives converge uniformly. That is the requirement. Correct? That is the requirement. Now, when you want to differentiate the series means you can reduce a series case to a sequence case, right? After all, series is just a sequence of partial sums. So when you want to differentiate term by term, differentiation is a local operation, right? You are differentiating at a point x, or take a point x naught, and you want to understand whether term by term differentiation is valid at x naught. Now, do you need uniform convergence of the whole domain? No, I just need uniform convergence in an interval around x naught. The uniform convergence hypothesis has to be satisfied in a interval around x naught. So it is sufficient that the sequence of derivatives converges uniformly on every bounded interval. If the uniform convergence hypothesis is satisfied on every bounded interval, it is enough. Correct? Is this clear? All right. Let us go back to the slide and So, let's see what the slide says. To justify term by term differentiation, recall that if Fn converges to F, then in order to conclude Fn prime converges to F prime, in order to conclude that Fn prime converges to F prime, we need that the sequence of derivatives converges uniformly on every closed bounded subinterval of the domain on which the functions are defined. This is the requirement, that the sequence of derivatives should converge uniformly on every bounded subinterval, right. Now, is this condition satisfied in our case? In our case, what is the story? In the present case, the series of derivatives is sigma jn prime t to the n. But what is jn prime? 1/2 of jn minus 1 minus jn plus 1. Remember, yesterday we proved an estimate, right? Mod jm of x less than or equal to mod x to the power m upon m factorial e to the power mod x. Correct? So, I can use that estimate over here and use Weierstrass's m test and finish it off. Correct? We have proved yesterday this estimate mod j, and so this series of derivatives converges uniformly with respect to x on every subinterval a b, thanks to the estimate mod jmx less than or equal to x to the power m upon m factorial e to the power mod x. It is exactly for this reason that yesterday I did that estimate. It is a crude estimate, but it is enough, because what I need here is just this crude estimate, that suffices. Correct? This completes the proof of the Schlomilch's formula. Is it clear? Schlomilch's formula, proof of Schlomilch's formula. The generating function for the Bessel's sequence of Bessel's functions has been computed in closed form. Similarly, when you take the sequence of Legendre polynomials, you can actually write down the generating function and you can find a closed form expression for the generating function. This is true for the equations, for all the famous equations. Correct? The generating function is computable in closed form, and a great deal of information is contained in these generating functions, and we can derive a number of interesting consequences out of these generating functions. When you study orthogonal polynomials, you will see that the generating functions are very important. You can see, for example, Sanson's book on orthogonal functions, right. So, now let us now derive one consequence of the generating function for the Bessel's sequence of Bessel's functions, and that consequence is the integral representation for the Bessel's function. The integral representation, the Schlomilch's formula holds for all t not equal to 0, t was just a fixed number and t could be a real number or a complex number, because as far as estimating is concerned, I took the modulus, so it does not matter. So, now since it is going to hold for all real or complex t, I am going to simply take my t to be e to the power I theta. I am going to take my t to be e to the power I theta, and then what do our left hand side becomes sigma j n x e to the power I n theta, right hand side becomes e to the power x by 2 into e to the power I theta minus e to the power minus I theta. What is that? 2 sin theta. So, you get x of I x sin theta. So, now how do I get my j n x out of this expression? Multiply by e to the power minus I n theta and do a term by term integration. Again, the estimate that we have derived will help you in this term by term integration. Correct? So, do a term by term integration with respect to theta. X is fixed. This time x is fixed. I am performing a term by term integration with respect to theta. So, you need uniform convergence with respect to theta. We are integrating. we are not differentiating. For integrating, the original sequence, the original series should converge uniformly, right. That also is available because of our estimate. So now you multiply both sides by e to the power minus I n theta and integrate. What is going to happen? J n x into 2 pi, integrate over the interval minus 1 to 1, right. Everything will disappear. When you integrate e to the power I k theta from minus pi to pi, you are going to get 0 except in one case, when k is 0. So when you multiply by e to the power minus I n theta, the only j n x term will survive after you integrate. So you will get 2 pi into j n x equal to minus pi to pi e to the power I x sin theta minus I n theta, correct. And so you will divide by 2 pi and you will separate the real and imaginary parts, correct. The real part is an even function, the imaginary part is an odd function. Cos of x sin theta minus n theta is an even function of theta. Sin of x sin theta minus n theta is an odd function of theta. When you take an odd function and integrate it from minus pi to pi, it is going to be 0. So only the real part will survive, and you get j n x equal to 1 over 2 pi minus pi to pi cos x sin theta minus n theta, and this, since it is an even function, I can write it as 1 over pi integral 0 to pi cos of x sin theta minus n theta d theta. This is the integral representation for the Bessel's function j n x, and this integral representation holds for integer values of n, not for non-integer values. This is a very special representation for integer values of n, correct. This was the original Bessel's original definitions of the functions that bear his name. So please write down the integral representation for the Bessel's function. So correct. This is a remarkable formula. The integral representation is much more convenient than the series representations for computational purposes. Integrals are easily approximated, series cannot be easily approximated. Take the exponential series, it converges for all values of x, e to the power x. But if you take x to be 10,000, then how many terms you have to take before you can get the value of the exponential function correct to several places, correct. So series representations don't lend themselves for computations. Integrals are easy to approximate. There are numerical techniques available to approximate. After all, you need to generate tables of, if you want to generate tables of Bessel's functions, you can't use series to compute. Though people like Gauss and Euler, they used to compute series and they used to get it up to several decimal places. But it's easier. I mean, integrals are easier to approximate and compute, correct. So here I will stop with the study of Bessel's functions, and we will move on to an application of Bessel's functions to a problem in celestial mechanics, correct. What do you want? The integral representation j n x equal to 1 over pi 0 to pi cos of x sin theta minus n theta d theta. J n x equal to 1 over pi integral 0 to pi cos of x sin theta minus n theta d theta. This formula is used more frequently in engineering, in modulation problems and other things. The integral representation is used more frequently than the series representation, okay. But we derived it from the series only. We used the series, we made estimates, we got the generating function, we got the properties, the recursion formula. So the series was a starting point for deriving all these things. Clear? The study of Bessel's functions is vast. I mean, we have just started the study, we have just spent an hour on this, and you should look up the book by G. N. Watson, A Treatise on Bessel's Function. It's a fat book, it's quite a tome, and you will get a lot of information on Bessel's functions. Watson is the name of the author, G.N. Watson. Same Watson of Whittaker and Watson. You know the book of Whittaker and Watson, Course of Modern Analysis, the same Watson. All right. All right, we will now move on to an application of the Bessel's function. All right. Yeah, any questions on this? Any questions? Okay. Oh yeah, it is a coefficient. It is a coefficient of the Fourier series only. What is the generating function? We applied the generating function. It is jnx e to the power I n theta. So jnx is the nth coefficient of the generating function when you put t equal to e to the power I theta. That's how we got it. That's exactly how we got it. We got it as a coefficient of Fourier series only. That's correct. Okay. As an application, we now show how Bessel's functions appear unexpectedly, or even I would say dramatically, in the analysis of a problem on celestial mechanics. Now, in celestial mechanics, there is this famous equation, let me call this Ke, called the Kepler's equation. What does the Kepler's equation say? Phi minus E sin phi equal to 2 pi t upon capital T. Phi minus E sin phi equal to 2 pi t upon capital T, where E is the eccentricity of the orbit of a planet. I am going to assume that the planet has an elliptical orbit, right. It is not true, I mean, it is not true that in the two body problem it will always be an ellipse. It could be any conic. Orbits of comets, some of the comets have parabolic orbits or even hyperbolic orbits. Such comets will never return. That's Halley's comet, for example, is an elliptical orbit, but the eccentricity is 0.96. It's almost a parabola. Halley's comet, the eccentricity is 0.96. It's almost a parabola. So some of a slight perturbation can very well cause it to become a parabola and not return. It happens. I mean, cometary orbits are perturbed severely by Jupiter and Saturn. And T is the period of the planet, and the angle phi is called the eccentric anomaly. This is an astronomical term. Well, I explain, you will ask me what is the eccentric anomaly. So let me tell you what the eccentric anomaly is. Take the ellipse, correct, and draw the auxiliary circle, x squared by a squared plus y squared by b squared equal to 1. What is the auxiliary circle? X squared plus y squared equal to a squared, right. So what is, and the ellipse has that representation, no? A cos phi, b sin phi. What is that angle phi? Take the point on the ellipse, take a point right above it, but on the auxiliary circle, and that angle for the position vector of that particular point on the auxiliary circle is the eccentric angle. In astronomy, you call it eccentric anomaly. Take the ellipse, take the auxiliary circle, take a point on the ellipse P, and take a point right above it Q on the auxiliary circle. Then Q is A cos phi, A cos phi, comma A sin phi. Point P is A cos phi, B sin phi. The point above it will be A cos phi, A sin phi. That phi is then the angle which the point Q, the angle of the position vector of OQ. I will show you a picture later, so it will become clear once again. But in astronomy, the term is called a eccentric anomaly. Okay, now we must derive the Kepler equation. What is the Kepler equation? Phi minus E sin phi equal to 2 pi little t by capital T. Capital T is a period. What is little t? I will tell you in a moment. But before we derive this equation, we must recall the Kepler's laws of planetary motion. What are the Kepler's laws of planetary motion? Law 1 says that planets revolve around the sun in elliptical orbits with sun at one of the foci. The second law says that the radius vector joining the sun and the planet sweeps out equal areas in equal intervals of time. And the third law says that the square of the period is proportional to the cube of the semi-major axis, and the constant of proportionality was determined by Gauss later, and he gives it in his book on astronomy which he wrote, Theoria Motus Corporum Celestium. The English translation is available in our library, Theory of the Motion of the Celestial Bodies. All right. So, the three laws of planetary motion. Okay. So, the first law is described by a picture. You see a picture of an ellipse. This is a sun over here, and there is an elliptical orbit, and the sun is at one of the foci, correct? The picture shows that over here, what is this point called? The point which is closest to the sun, perihelion, and this particular point is the aphelion, correct? What will be the, when you take the earth and the moon, what is the point on the moon's orbit where it is closest to the earth? It is the perigee and the apogee. The perigee and the apogee for the earth moon system, perihelion and aphelion for the planet and the sun, and if it is Jupiter and its satellites, it is going to be perigeo and apogeo. It's going to be perigeo and apogeo for the Jovian satellites. Jupiter, Jove, Jovian satellites, right? The satellites of Jupiter are called Jovian satellites. Right? Ganymede, Callisto, Io, Europa. I'll tell you the spelling later. Jovian, Jovian, Jovian. Okay. Here is another picture depicting the same thing, and the semi-major axis is described very clearly in this picture. Right. The two foci are indicated, the perihelion and the aphelion, correct? Perihelion and the aphelion, right? This is the first law, Kepler's first law, right? It took a long time. It was a very arduous task for Kepler to arrive at these laws. The history is very interesting. He had a lot of problems, and he went to the greatest astronomer of his time, Tycho Brahe. I mean, I think I will not talk about this. You should read the books on astronomy. It's absolutely exciting. And here is an illustration of the second law. The second law says that the radius vector joining the sun and the planet sweeps out equal areas in equal intervals of time. Here the planet is moving faster, and it covers a greater arc, but the distance is smaller, and whereas here the distance is larger but this arc length is smaller, correct? The areas will be equal though. This radius vector sweeps out equal areas in equal intervals of time, correct? This is expressed by saying that the dA by dt equal to h by 2. So here is, so you take a point, take a reference point on the orbit, let us say the perihelion, and from the perihelion you measure the areas of the sector, right? So AT is the area of the sector. So you fix this particular radius vector, and as the planet moves, you keep measuring the area of the sector. So dA by dt is constant. This constant is h by 2. And what is this really indicating, this equation? It is a reflection of it is a mathematical expression for the conservation of angular momentum. This is really the law of conservation of angular momentum. It takes this form. Remember that this law, the Kepler's second law, is just a reformulation of the law of conservation of angular momentum. Okay. The third law is t squared is proportional to a cube, where t is the period and a is the semi-major axis. All right. So here is another picture for you of the second law, the sun and Mars. The orbit of Mars is what gave Kepler maximum difficulty. And then here is one more picture which these people have scanned for me. It's very beautiful job has been done. So, showing these sectors and how they change and all those things, alright. Alright. So, we shall not derive these laws here, it is not difficult to derive them. You can look up the book by Danby, Celestial Mechanics, that is a very good book on celestial mechanics. A derivation is also available in the book by Ostberg and Finney. You have seen the book by Ostberg and Finney, I showed you, and in that book on page 201 to 204 you will see a derivation of the Kepler's laws. So, you can consult that. Another book is McCuskey's book on Introduction to Celestial Mechanics. So, you can consult any of these books if you will, and we shall not discuss the derivation here. I mean, that will be another chapter really on differential equations. In differential equations there can be several chapters and time is short and we can't do everything. This is something that you can read on your own, it's pretty easy. I mean, it's available in Osberg and Finney, it's quite easy, very readable account of. Alright, alright. So, let us go to the derivation of Kepler's equations. So, what is Kepler's equations again? It is theta minus E sin theta equal to 2 pi t by t. It should be phi, no? Sorry. It is the angle phi, not theta. Let me just make a correction, please. It is phi minus E sin phi equal to 2 pi t upon capital T. So, the figure, let me first show you the figure, okay. Let me first show you the figure. Here is a nice picture showing you the ellipse and the auxiliary circle, right. There is a picture showing the ellipse and the auxiliary circle. This is the point Q and the point S right above it. The perihelion is P and the aphelion is P prime. The focus is F, correct. And the angle PCS is the angle phi. You can see very clearly now in this picture what is the eccentric anomaly, and the angle theta is called the true anomaly. The angle theta is called the true anomaly and the angle phi is called the eccentric anomaly, alright. Now, let us assume that our time starts when the planet reaches the perihelion. After the planet crosses the perihelion, you start your stopwatch and then it has come up to the point Q in time t, correct. It has come, it has from P to Q, it has taken time little t, right. Now, this angle theta and this angle phi are functions of t. Our problem now is to determine this angle phi of t as explicitly as possible. The problem, the complete problem of the solving the two body problem completely means determining theta of t and phi of t explicitly as functions of time, correct. This is the problem, alright. So, let us go back to the previous slide. So, the lemma, so let me state a lemma. You are taken P prime P is the major axis. I told you P is the perihelion and P prime is the aphelion. C is the center. Q and S are corresponding points on the ellipse and on the auxiliary circle on the same side of the major axis, right. And then this angle PCS is called the eccentric anomaly and PFQ is called the true anomaly. So, I explained to you in the picture all the terms, correct. And the lemma says area sector PFQ, this area sector PFQ divided by the area sector PFS equals area of the ellipse upon the area of the circle, which in turn equals B by A. Area of the ellipse is pi AB, area of the circle is pi A squared. So, area of the ellipse upon area of the circle is B by A. So, the lemma says area sector PFQ upon area sector PFS is B by A. This is what we want to derive. All right, this is the problem. All right. So now let us look at this area. So how would you do that? You would use calculus to calculate the area of PQH. What is the area of PQH? Write the equation of the ellipse, y equal to b by a root of a squared minus x squared, and you have to integrate from here to there, correct? And what is the equation of the circle? Y equal to root of a squared minus x squared. You have to integrate from here to there, correct? And you can calculate the area of the sector PQH and area of the sector PSH using calculus, correct? Is that right? Now what are you going to do? How are you going to calculate the area of the sector PFQ? It is the area of the sector PQH minus area of the triangle HFQ. Is that right? What is the area of the triangle HFQ? It is half HF times the height. And then what is the other sector that you have to calculate? PFS. What is the area of PFS? Area of PSH minus area triangle HFS. What is the area of triangle HFS? 1/2 base into HS. So you see, both the triangles have the same base and their heights HQ upon HS is B by A. Both the sectors have ratio, the areas B by A. The ratio of the sectors PQH upon PSH, that area is B by A. The triangles FQH and FSH also have ratio B by A. Take the difference. Therefore, you take the difference and you will get area sector PFQ upon area sector PFS is B by A. That is a proof. That is a proof, correct? And so let me just show the proof in the slide. So here I have calculated actually area triangle HFQ, which is half base into height. Area triangle HFS is half base into height. You take the ratio, it will be B by A. Using calculus, show that the area sector PHQ is B by A times area sector PHS directly, and subtracting you will get the result. Absolutely straightforward calculation using a little geometry and using a little calculus, integral calculus, correct. So lemma 1 is proved completely, all right. Could you please write down this particular expression, or maybe let's see whether we can directly do it without with a picture only. Now areas, tell me, why do we bother about calculating area sector PFQ? The reason is very simple. We are going to use Kepler's second law. Area sector PFQ divided by the area of the ellipse will be what? You have, what does Kepler's second law say? That the rate at which the rate of change of sectorial area is constant, correct. So if I take two sectors and take the ratio of the areas, it will be the same as the ratio of the time it takes to cover those two sectors, right, the arcs. Is that right? That is Kepler's second law. So now we have area sector PFQ. Area sector PFQ upon the area of the ellipse. What is that going to be? It is going to be little t by capital T, because to complete the ellipse you are going to take capital T. The whole ellipse is also a sector, no? And the corresponding time to complete the whole ellipse is capital T. And this much from P to Q it takes little t. So area sector PFQ upon area of the ellipse is what? Little t by capital T. So little t by capital T will be area sector PFS upon area of the circle. Look at this equation here. Put the area of the sector on the right hand side, correct. So, what do we get? Little t by, okay, once again, are you following what I am saying? Area sector PFQ divided by the area of the whole ellipse is little t by capital T by Kepler's second law, correct. On the other hand, we have area sector PFS divided by the area of the circle. Area of the circle we all know, pi a squared. So, we get the equation area sector PFS equals T upon capital T into pi a squared, correct. Now, our job is to find area sector PFS. What is the area sector PFS? It is the area of the PSC minus area triangle PFS. Remember, what are we trying to find? This is what we are trying to find, right? Area sector PFS. That is what is not, area circle is pi a squared. Everybody knows that. Area sector PFQ upon area of the ellipse is little t by capital T by Kepler's second law. What is required now? Area sector PFS. What is area sector PFS? It is the area of the sector PSC minus area triangle CFS. What is the area triangle CFS? Half base into height. What is the base? FC. What is FC? AE, where E is the eccentricity, the base is known. What is the height? HS? Height HS is A sin theta, A sin phi, excuse me. Phi is the angle and A is the radius. So, height HS is A sin phi and the base is AE. Half base into height is the area of the triangle and the area of the total sector PSC. What is the area of sector of a circle? It is A squared by 2 into, what is the area of a sector of a circle? Half A squared into the central angle measured in radians, correct. So, we have everything, we just have to put all the pieces together and get the result, correct. Alright, let us go ahead and let us finish it off, right. So, that is what I said. The first slide simply says area sector PFQ upon area of the ellipse is T by T. Other thing that I said is that is the first thing, alright. So, after using the lemma, we are now reduced to area sector PFS equal to pi T by A squared times A squared. PFS. PFS, once again, let me show you, is this PFS. PFS. That will be PCS sector minus triangle SFC, correct? All right. So, now we are up to this point. Area sector PFS is pi T by T A squared. Now, we have to calculate area sector PFS, that is the area of the sector of the circle minus the area of the triangle. Area of the sector of the circle, I just finished saying, is half A squared phi. Phi is measured in radians and area of the triangle is what? Half base into height. What is the base? AE. What is the height? A sin theta. There it is. And so, you have to compare these two results, we get A squared will cancel out, pi T by T equal to half phi minus half E sin phi, right. Therefore, if you clear the fraction 2, you will get phi minus E sin phi equal to 2 pi T upon capital T. This completes the derivation of the Kepler's equation. Our job is now to find the inverse function. Phi, this gives you phi as a function of time implicitly. Here this gives you phi as a function of t implicitly, we need it explicitly. In other words, you have to find the inverse function. All right. Okay. So, now how do you do this? How do you know that this function is invertible? How do I invert it? I have to apply the implicit function theorem, or rather than appeal to implicit function theorem and big theorems, let us look at the simple case. Let us write f of phi as phi minus e sin phi. So, f of phi equal to something, and I want to find phi, right. I want to invert the function f. So, when is the function invertible? You have a function of a real line, phi is on the real line. So, you differentiate the function, phi prime 1 minus e cos phi, 1 minus e cos phi. E is the eccentricity of the ellipse, it is between 0 and 1. So, 1 minus e cos phi will never be 0, So, the derivative is always positive, the function is strictly increasing, and phi goes to plus infinity, it goes to plus infinity, and when phi goes to minus infinity, it goes to minus infinity. So, with the intermediate value theorem, the function assumes all real values and it is a strictly increasing function, the derivative is positive. So, the inverse function exists and it is differentiable infinitely often. The inverse function is a C infinity function, correct. We have to determine the C infinity function. So, the inverse function exists, it is infinitely differentiable. How do we determine this? That is a problem. Is it clear what the problem is? All right. So, the phi t which is so the phi t is f inverse of 2 pi t by capital T. It is actually a smooth function, it is infinitely differentiable. Now, note that when after the planet has reached the perihelion, it moves on, correct, it moves on to this position. When time little t becomes capital T, it returns to the perihelion, right. So, when t changes additively by capital T, that is when little t becomes little t plus capital T, what happens to the angle? Angle increases by 2 pi, na? One full circuit is over, it is starting the next circuit. So, when t changes to t plus capital T, phi changes to phi plus 2 pi, correct. So, therefore, if I subtract phi t minus 2 pi t upon capital T is a periodic function of period t, because when little t changes to little t plus capital T, phi changes to phi plus 2 pi. So, when you take the difference in red, I have actually given you the algebraic reasoning why the phi t minus 2 pi t upon capital T is a periodic function of period capital T, correct. Now, we have a periodic function of period t. What are we going to do with it? We are going to write out its Fourier series. We are going to write out the Fourier series for phi t minus 2 pi t upon capital T, correct. Now, let us proceed a little further. Let us get one more piece of information about this function phi. What is the function? What is the function f? Let us try to remember, f of phi equal to phi minus e sin phi. Odd function is an odd function, agreed? Do you agree with me that the inverse of an odd function is an odd function? What is the inverse? How do you get how do you get the graph of an inverse function? By reflecting it about line, right? About the line y equal to x. So, graphically you can convince yourself that if you take an odd function, then the inverse function will also be an odd function. You can also prove it analytically, but the definition of the inverse function and the definition of an odd function, correct. So, the function phi is an, what is the function phi t? Phi t is f inverse of 2 pi t by t, and f was an odd function. So, the inverse function is an odd function. So, now we have an odd function, not only is phi t minus 2 pi t by capital T periodic, it is a difference of two odd functions. So, is a odd function. So, now we have a odd periodic function of period t, remember, all right. So, when you have an odd periodic function of period t, how does a Fourier series look like? It will be a Fourier sine series, absolutely. So, it is a Fourier sine series. So, you have phi t minus 2 pi t by t is n from 1 to infinity bn sine 2 pi n little t upon capital T. And what is the coefficient bn? The coefficient bn is given by 2 upon t integral minus t by 2 to t by 2 phi t minus 2 pi t upon capital T sine 2 pi n t upon t dt, correct. Is that clear? And this is an odd function. So, this is an odd function, sine is an odd function, the product is a even function. So, it will become 4 upon t 0 to t by 2, correct, all right. So, it becomes 4 upon, so bn becomes 4 upon t integral 0 to t by 2 phi t minus 2 pi t upon t sine of 2 pi n t upon t, correct. Now, integrate by parts. I have now written the sine as a derivative of cosine and with the appropriate, adjusting the appropriate constant, so that you can easily integrate by parts. Integrate by parts and push the d dt over here, you will get the d dt of phi t minus 2 pi t upon t dt, correct. And so, there will be two terms here, right, d phi by dt minus, what is the derivative of 2 pi t upon t? It is simply a constant. And so, for the second piece, you are integrating a cosine, it will become a sine, and at the boundaries it becomes 0. So, you are simply left with 2 over pi n 0 to t by 2 cos of 2 pi n little t by capital T d phi by dt dt. Is it clear? So, the Fourier coefficient has been brought to this nice form. Now comes the real trick. Now comes the real trick. We have to use phi as a variable of integration. We use phi as a variable of integration, and at when little t equal to 0, phi is 0. We are at the perihelion, the angle is 0, and when after half the period you are at the aphelion. What is the eccentric angle for the aphelion? Pi. So, the variable of integration will become, variable of integration is taken to be phi, and phi takes the values from 0 to pi when t goes from 0 to t by 2, correct. And so, it is cos n, what was it, what did the previous slide say? It was cos n 2 pi little t by capital T. Now, what is 2 pi little t by capital T? Phi minus E sin phi, correct. 2 pi t upon capital T is phi minus E sin phi. So, that is what has happened here, cos n into phi minus E sin phi d phi. Lo and behold, you see the Bessel's function evaluated at NE. And so, the Fourier series for phi t minus 2 pi t by t is sigma n from 1 to infinity 2 upon n Jn Ne sin 2 pi nt upon capital T. Series of this form are called Kapton series. For details, you should see Whittaker's book, Watson's book. On the treatise on Bessel's functions. So, this is a remarkable expression for the eccentric anomaly, for the expansion of the eccentric anomaly as a Fourier sine series. There are a variety of expansions available. You could expand the eccentric anomaly as a power series, right. If you write it as a power series, the power series in E, I can expand the Bessel's function as an infinite series and rearrange, and I will get a power series in E. That power series will not converge for all values of E, it will only converge when the value of E is less than 0.66. Now, Cauchy was puzzled as to why is it that the series only converges for limited values of the eccentricities. If you, I already told you that the orbit of Halley's comet is 0.96, it goes beyond the scope of the power series expansion. The point is that the function phi in the complex domain has a singularity that is causing the radius of convergence to be limited to 0.66. But this problem was studied by Cauchy in great detail. The theorem of Roche, which you see in complex analysis, appeared in connection with this kind of a problem, the Roche's theorem, right. So, with this nice application and with this beautiful derivation of the eccentric anomaly in terms of the Bessel's, in terms of as a Kapton series, I will close this course, and thank you very much for coming here and for listening to me, and I hope I entertained you enough. And if you are not entertained and if you are bored, I apologize to all those people. Okay, thank you very much.